Let us consider a problem now. Say we have a cylinder with a long pipe at the bottom of this cylinder. This pipe here has a length L, its radius is small r, the cylinder here has a diameter of 2r, and fluid is present up to a height of capital H from the pipe. The fluid has density rho and viscosity eta. Consider that this small radius, small r, is very less than r. This is nothing but something. This something, if you recall, comes from the Bernoulli's principle. This basically states that the Torricelli's law is valid in this case. What was the Torricelli's law when we discussed Bernoulli's principle? The Torricelli's law stated that this fluid basically free falls through this height when this condition holds. This condition is nothing but the area of the pipe, area of cross section of the pipe is very less than the area of cross section of the cylinder. This is nothing but this. Provided these conditions, we are supposed to find out height of the fluid in the cylinder as a function of time. This is what we are supposed to find out. Let us proceed with this problem. Let us assume any height, small height, or any height, small h, at any point of time, say t. At any time t, let's say we have a height h of the fluid. Obviously, this height is going to vary from this capital H to a 0, which is at this base level. So what we are doing is assume h and t. Now, what is going to be the pressure head? If you consider this pipe similar to the problem the concept we discussed a little while earlier, this pipe is nothing but a pipe which we considered then with some pressure gradient, which is some pressure being applied at this point, and this point, let's say the pressure is P0, that is the atmospheric pressure. At this point, the pressure is going to be P0 plus the hydrostatic pressure due to this height of liquid rho. So the pressure head is going to be equal to P0 plus rho g h, this quantity minus the P0 which is on the other side. This is going to give you nothing but the quantity P that we discussed earlier. What we discussed earlier was about the volume flow rate. That is also what we discussed. So what we really need to do here is apply the concept of continuity. That is, whatever height is getting decreased here or whatever fluid is lost here is coming out from this pipe. This is the basic concept that we are going to follow. So what is the volume of the fluid coming out, or the rate of volume which is coming out from here? This is nothing but Q dot. This into dt is going to give us the volume, because Q dot is a rate. Q dot is nothing but volume per unit time. So this is need to be multiplied with time, so to make it a volume quantity. This is equal to the decrease in volume in this cylinder. The decrease in volume of fluid in this cylinder is nothing but the cross-sectional area of the cylinder times the little height that got decreased when the fluid is flowing out of the pipe. This is going to be nothing but pi r square times dH, considering a small drop in height of dH. This is our governing equation. Now what is this Q dot going to be? We derived earlier that this Q dot is nothing but P by 8 eta L by pi r to the power 4. This times dt. This is equal to minus pi r square dH. Now here this P is nothing but this quantity. So we will be having rho GH times this pi r to the power 4. Note that this R, I have made a mistake here. This capital R is not going to be capital R. There we considered that our pipe radius was capital R. Here our pipe radius is small r. So this is going to be small r to the power 4. Please be very careful about these symbols, because we never know that when a formula is remembered, we remember the exact quantities what we took in those formula. But in actual situation, the values or the symbols might be changed. Like here, the small r is replacing the capital R what we had earlier. So this is going to be small r to the power 4. This divided by 8 eta L. L is the length of the pipe. This is equal to minus pi r square dH. So now what we do is separate out. There will be a dt also here. We have already separated out these variables. What we need to do is take this h term to its rightful location here and then integrate both sides. So if we do that, we will be having dt into a huge number of constants. Let us cancel off this pi. Say this is rho g into small r to the power 4 divided by 8 eta L into capital R square. This being equal to minus dH by h. Now what we do is integrate both sides. This has to be integrated from 0 to time capital T. This capital T is the time at which the entire cylinder will be empty. That is what we needed to find out. Or rather, if we do not put this integration as a definite integral, what we will actually find out is the time as a function, the height as a function of time. So on this side, we will be having ln of h with a negative sign being equal to rho g r to the power 4 by 8 eta L r square times t. This negative sign can be taken here and this can be converted to an exponential form like this. H will be now equal to e to the power minus rho g r to the power 4 by 8 eta L r square, this entire thing times t. Note that when we perform this integration, we have also neglected a constant of integration that comes into the picture. That constant of integration cannot be neglected. Say this constant of integration is, say, b. So now when we integrate this like this, or if we make it to be ln of b, this will simplify things, as this can be represented as a constant here. This is what we have. Now how do we determine this constant b? So this is our general solution.